You see averages everywhere, right? The average temperature, the average price, the average score. They're supposed to give us this nice, simple middle point. But here's the thing. The average all by itself is kind of boring. It's like a story with only one character. The real action, the interesting part, is in the spread around that average. And understanding that spread, that variation, that's where the good stuff is hiding.
To really get why this is so important, let's imagine a scenario. You've got two athletes, and on paper, they look like twins. Both are averaging a solid 20 points a game. But if you had to put your money on one of them having a solid game tonight, who would you pick? Just based on that average. It's a total coin toss. We're clearly missing a huge piece of the puzzle.
And here is that missing piece. Take a look at their actual game-by-game scores. Player A is, well, Mr. Reliable. 19 points, 21 points, 20 points. Always right there, hovering around that 20-point average. But player B? Whoa. Player B is a total roller coaster. One night it's 5 points, the next it's an incredible 35. See? Same average, totally different story. We need a way to actually measure that consistency, or, the lack.
Okay, so how do we put a number on this idea of spread? The first thing that comes to mind seems super obvious, but as you're about to see, it leads us straight into a mathematical wall.
So your first thought, and it's a good one, is to look at the deviation for each score. It's a simple idea. Just how far is each individual score from the average? So for players A's first game, they scored 19. The average is 20. So that's 1 point below the average, a deviation of -1. The next game, 21 points. That's 1 point above the average, a deviation of +1. Seems simple enough, right?
So the logical next step is to just find the average of those deviations. Let's try it for player A. We have a -1 plus a +1 plus a 0 from that last game. We add them up, and we get a very specific and very unhelpful number. 0. And this is not a coincidence. This isn't a fluke. It's just how averages work. The positive deviations and the negative deviations will always, and I mean always, cancel each other out perfectly. It doesn't matter what your data looks like. So our first, most logical approach has led us to a dead end. We need a better plan.
But statisticians, well, they're pretty clever folks. They came up with a really slick way to get around this whole canceling out problem, and it just involves one little trick from middle school math.
The solution is actually pretty genius. Before you average the deviations, you square each one. Think about it, right? A negative number squared becomes positive. A positive number squared stays positive. So that -1 deviation becomes a +1. Suddenly, poof, nothing can cancel out anymore. The problem is just gone.
And this new number we just created, the average of all those squared deviations, that has a name. It's called the variance. And it's our first real working measure of spread. A big variance means the data's all over the place. A small variance means it's all bunched up neatly.
But there's a deeper, more powerful reason why squaring is so great. As one Reddit user pointed out, it's not just about getting rid of negative signs. Squaring gives way more weight to the outliers. A score that's 2 points away from the average, that adds 4 to the variance. But a score that's 10 points away, that adds 100. It gives a much, much louder voice to the extreme values, which is exactly what you want when you're trying to measure how spread out things are.
Okay, so we've fixed the math problem, but we've accidentally created an interpretation problem. If our athlete scores in points, their variance is now in squared points. If we were measuring height in feet, the variance would be in squared feet. It's just weird, and it doesn't really mean anything intuitive. What even is a squared point? How do we get this back to something we can understand?
Thankfully, there's one last super simple step that brings this number back down to earth and makes it all make sense again. We just take the square root of the variance. That's it. We literally just undo the squaring we did earlier. This new number is called the standard deviation. And by taking the square root, we bring our measurement of spread back into the original units. So squared points become points again. This is the number we can actually work with.
Now, for anyone who's ever cracked open a stats textbook, there's probably one more confusing detail that's been nagging at you, and it's all about the difference between looking at some of the data versus all of it.
You've probably seen two different formulas floating around. Sometimes you divide by n, the total number of things, but other times you divide by n-1. So what's the deal with the -1? Why the two different formulas?
Well, this little tweak is called Bessel's correction. And here's the basic idea. A small sample is just less likely to catch the true extremes of a whole population, right? If you only survey 10 people about their height, you're probably not going to find the shortest and tallest people in the entire country. Because of that, a sample tends to make the spread look smaller than it really is.
So by dividing by a slightly smaller number, n-1, we're basically giving our final number a little nudge upwards, making it a more honest guess of the real spread. This quote makes it super clear. Just imagine you take a sample of one single person. Well, their score is the average, right? So their distance from the average is 0, which means the variance is 0. But that's nuts. It obviously doesn't mean there's zero variety in the whole population. The n-1 correction basically says, hey, a single data point tells you nothing about spread, and it helps correct for the fact that any sample gives you an incomplete picture. All right, so we've done all this math. We've gone through variance and Bessel's correction. What's the big payoff? What does this final number, the standard deviation, actually tell us? Well, this is where it gets really, really useful.
Put simply, standard deviation is a universal yardstick for risk and consistency. Think about investing. An investment with a low standard deviation has predictable, stable returns. It's low risk. One with a high standard deviation, its returns are all over the map, a total wild ride. That's high risk. It's one single number that tells you how uncertain something is.
And for a ton of data in the real world that follows that classic bell curve shape, things like test scores or people's heights, there's this amazing rule of thumb you can use. It's called the 68, 95, 99.7 rule. About 68% of everything will be within one standard deviation of the average, about 95% will be within 2, and almost everything, 99.7%, will be within 3.
This gives us a fantastic mental shortcut for spotting what's normal and what's not. If a data point is within one standard deviation, it's common, it's ordinary. But if something is 2 or especially 3 standard deviations away from the average, whoa, now that is rare. That's an outlier. That's a signal telling you to pay attention because something unusual is going on. So let's bring it all the way back to our athletes. With this new tool, the answer is just staring us in the face. Player A, Mr. Consistent, has a standard deviation of just 1 point. His scores are always tightly packed around his average. Player B, our roller coaster, a massive standard deviation of 15 points. Boom! Now we have one number that tells the whole story the average was hiding. We know exactly who's more reliable.
So here's the bottom line. An average tells you the center of the story. The standard deviation tells you the plot. It tells you if it's a calm story or a dramatic one. So the next time you see an average reported somewhere, you'll know that's not the end of the story. You have to ask the crucial follow-up. Okay, but what's the standard deviation?